So, hello everyone and welcome back. In this session of the course we will get introduced together to the multi-domain simulations, which is a little bit of a sophisticated case compared to what we've seen before, but it's also very practical and it's very nice to have it as a tool in your skill set, how to simulate a fluid flow with also a solid domain with conjugate heat transfer or some interfaces between the two domains. So let's go ahead and see what this problem is carrying for us. So as you can see here, the domain is representing some kind of a compass shape. We have water flowing here from left to right, or we call it in the boundary conditions, as you'll see in a minute, west to east, and then you have in the bottom you have air flowing from the south to north, or from the bottom to top, and you have then kind of a membrane or a shell in between that's also taking the interfaces of both domains, upper and lower. So we will go through this step by step. I just wanted to show you here that it's a very interesting problem. You have crossings of fluid interactions. So let's go to the terminal and see how to run such a problem and also how to set it up. So if we go to the terminal, now we are in a directory where your working directory where you have the code. Open the code and go ahead to tests, and if you list the tests, then you can go to RANS because it's a turbulent flow case, and then you will find membrane within this list. So the case is called membrane, or 3D, 3-domain membrane, because there is also 2-domain membrane that we will see it later. So this case is fairly simple, or let's say it's much simpler than it looks like, but the flow topology and the interfaces between the domains, so you have 3 domains, is what makes it a little bit more sophisticated than the cases we saw before. Otherwise, it's very straightforward case with a control file, but we will talk about that in a second, why this case has 4 control files instead of 3. But before we dive into these details of the problem setup, let's go and compile the code. And in order to compile the code, we need to go to sources. So we are 3 steps back exactly. So we have membrane, RANS, tests. So if we go 3 steps back and then we get into process, then we can kind of make sure that we don't have anything from the past that's clean. And since this case is quite sophisticated, it will be quite slow to run it on a single processor. So it's much better if we run it on in parallel mode. And for running the problem in parallel mode, we have to put this command, as we learned before, mpi yes, which gives you the option to run mpi run before your process. And one last thing here is that what we specified before is that the case directory, which we need to make sure that if there is any user mod function, then it's hooked up to the process while running the problem. So we go to tests, RANS, or you can also, instead of this, you can copy paste the root path and then paste it here, and then have it here. So RANS, and then you have membrane, and if you click OK, good. So the code has been compiled now. Now we can go back to our case through either if you have an alias, or as we said before, if you do cd dash, then you go back to your original or to your previous path. Now we're inside membrane. Remember, as I told you before, I prepared an automated script or automation script that can run the whole problem for you one step after another. And that's just to simplify the process, just so you don't have to enter anything or everything manually by hand. But you're free to do so if you like it, or if you feel that it engages you more. I just put it there for two reasons. One is if you know the process and you know what you're doing, you can run it much faster like that. And second, if you face any problems, or maybe you made a typo and you don't know what's happening, but you still want to run the problem, and then maybe through the scripts that will be generated or the log files that will be outputted, you will realize where the problem was. So in both cases I made these automation scripts that are two in each of the cases. In this course we'll have these two scripts. One is clean case and the other one is run case. So obviously if you open clean case here, for example, you remove any old output files, faces, monitoring points, backup files, readme or control files. And usually you don't remove the control file, but I will show you in a minute why I put here the control file, because not that I'm removing the input file itself, but because here this is usually in this case a soft link. So it's just a case specific detail, because if you go back here, see already the control files are named with numbers. So control 5, control 0, control 1, 2, 3. And when we make a soft link, if you want to clean the case, then the soft link will stay control, not control.0 or control.number, but the control will stay, and then it will be always pointing to one of these control files. So it's just kind of a small detail that I added here just to make the process faster or smoother, that you don't have to input anything by yourself. So before we run the case, let's discover together what this case has actually. So if we go into control 1, let's start with control 1. And control 1, you will find that we have, as I showed you here, we have 3 domains. Maybe it's not very clear from this picture because it has the velocity contours plotted on top. But I will show you in a minute what this case is representing and what are the 3 separate domains that are laying on top of each other. The first one is the upper domain, which has this inlet here and this outlet, and it has only this one direction, the plate and inlet outlet, and you have this bulk region in the middle. And then the bottom domain, or what we call here the lower domain, you have the inlet from here, from the south inlet, and then outlet from the north, and then you have the same bulk region for the flow to be advected through this. So it's just like it's like a heat exchanger. You can think of it as a heat exchanger, but the difference is we have first of all, we don't have explicit mixing of the flows. They're just laying on top of each other, and the mixing is happening through temperature. So the temperature is affecting, from the top domain, is affecting the membrane, which is something that it's insinuated in between. And temperature from the lower domain is also affecting, from the top surface, the membrane from the bottom. So everything will become very clear when we visualize them in ParaView, but I just wanted to give you some outline. So if we go back here, we will find the first domain, which is upper, and then heat transfer is yes, because we're transporting energy. And then you have all the parameters that we talked about before: monitoring points, physical parameters, blah blah blah, numerical parameters. And then you have some maybe details about the turbulence model, if you have turbulence. So in this case, you have in the upper domain and lower domain, I guess more or less the same medium, but doesn't matter. You can have always air here, water there, and then see how the advection is happening between the two domains. You can see clearly the difference. But you get the idea here that the parameters are exactly the same. It's a very normal control file. Has all the parameters that we talked about before, and then you have here these turbulence quantities that are initialized by specific value, because here that's the upper domain has fluid flow. So it's a turbulent flow, and you add these turbulence parameters as the initialization points, so you can advect the flow with the turbulence model that is specified here. And the same goes for the lower domain. And then you can see here you have monitoring points and everything exactly the same. And you have your initialization and boundary conditions with the values to be initialized with. If you go to domain 3, you will find that the membrane itself has the same control file. The only thing that's missing is the turbulence model, because that's a solid. It doesn't even have fluid to advect. So it's the only reason that the control file is written in the same way is that TFlows is expecting the same routine, or it goes through the same loops, and it tries to find all of these parameters, and it deals with it as exactly as a fluid domain, but then it switches off the conservation of momentum, conservation of mass, the continuity and momentum equations, because there is no flow in this layer, or the solid domain obviously, and then it affects temperature, or if you have something else to deal with. But in this case we have only temperature, and then you will see in the control and the output file, once we run the problem, that there is nothing being advected and all the residuals are nullified except the temperature. And here you don't also see the values for the turbulent quantities, because you don't have turbulence specified in the domain. So that's it. You have now 3 control files, 1, 2, 3, upper, lower, and the membrane. And now there comes the control 0, which is the global control file. That's the global control file that kind of tells the code that we have 3 domains. And then you have this new key parameter here, or keyword, number of domains 3. Then it tells it that you take 3 control files. You have to search for 3 control files, and each of these control files will have like a process which is running the program in parallel. You run the first domain, the second domain, and the third domain. So it's actually sequence. It's not really running in parallel, but you can run this sequence in serial or parallel, as we will see. And what this global file has is just a number of time steps which is shared between all the domains. Save time interval, because there is no reason to save the files in one domain in a different way. You just always want to have the same comparison, how the flow or the temperature is affected through all the domains at the same time. And the backup save interval is the same also. The time step is the same for all domains. And the last thing here is the tolerance for simple algorithm, because there is no sense, or there's no point in, let's say, having a stopping criteria or a convergence criteria that is different for each of those domains. So you have also the same stopping criteria for the 3 domains. And here these 4 lines here are just saying to the code that the interface conditions, or the interface between the domain which is upper, the domain that's called upper, will have the bottom of this domain. The bottom of this domain will be linked, or will have the interface of the top of the membrane. So membrane is the domain that is in the middle, and it has an upper domain on top of it, a lower domain below it. So it kind of makes sense, right? That so that's actually a technical detail that you can always go and check in the source code. But it's an algorithm that tells the code that you have to have an interface between these domains to transport something, right? Otherwise they are kind of detached. Every domain doesn't know anything about the other domain. So this is what links them, what makes the information travel between the domains and then be coupled by one another. And the same goes for the membrane, that from the bottom side of the membrane then comes the top side of the lower domain. So it's kind of a stacking mechanism, and then you're just specifying to the code where are these interfaces, so it can kind of locate where things are. As we explained all of this, then you kind of expect that we have a mesh, and then we need to, if the mesh is locally generated in TFlows, we don't have to convert it. If the mesh is from an extended software, then we convert it, which we have here, convert for, these convert scripts for upper, lower, and membrane. And then if you're running the problem in parallel mode, then you divide the domains into the same number of processors, or into the same number of subdomains to be computed on the same number of processors. And here you have modules, which is the geometry. Basically, if you open this file, it's a Gmesh file that you can always interact with if you like. If you want to change the geometry, want to change the mesh, quite straightforward to open them in Gmesh and play with them. But here, for the sake of the relevance and the time limitation of the course, as I said, I created these run scripts for you that it does all the job for you. It starts again by cleaning any old files, linking binaries, and then you have here, we're extracting this mesh that is generated by Gmesh already, and then converting the mesh by the local into the local format of tflows, and then you run the problem in serial or parallel. Here there is a small difference to the previous cases, and I actually updated the source on GitHub, so you can have the same feature again, or you have both features, but since I updated this run case, then you can have it always in a smoother way than we did in the last session. So what changes actually is just instead that you run case like this, and once you run it, then you kind of wait until the mesh is converted or extracted, and then you pass the word serial or parallel, so you can tell the code in which mode it will run process, which is also a process, but just that you're not confused. I'm talking about process, the program in tflows that runs the algorithm, the numerical solver. And what happens here now is that I just updated the sources that you can kind of pass this word up front. So you can pass either serial here, or you can say parallel from the beginning. So you don't have to interact anymore with this script. It's just started. It will just start the process automatically. But before it starts, I want to show you in what type of, how many processors it's going to divide the domain into. So you can see already here upper is 4, or you can also do something like that. You can make divide by this asterisk here. I can open all the files at the same time, and you can just shuffle between them by colon. You can see here on top, on bottom left, that I put colon and n, small n. Then if you hit enter, then it moves you to the next file, which is the lower domain, also divided into 4 subdomains. Then colon n gives you the last one, which is membrane, also 4 subdomains. You have to make sure that you have the same number of subdomains specified, otherwise you will have a problem. Now we can run the case already. I guess we're in a good shape now that we know all the essentials about this, the case setup. And as I said, you can pass already the word parallel from now. Then kind of it extracts the meshes because they are already generated, but they were in GZ or the kind of zipped format of a file. And then it gunzip this, extracts the mesh, then it puts it into MSH, which is a format, fluent format in standard. And then it converts it into the local format of tflows, divides the domain into 4, and then starts the solution. So while the solution is running, you can see already here, I'm not going to stop the solution, but maybe we can play it safer by opening another tab, and we can tail this, the sources, and we can tail the log file, sorry. And while we're tailing the log file, I can maybe explain here something a little bit. So as I said, the upper domain, lower domain, or maybe it starts with the lower domain and upper domain as the sequence in the control file. So you can see that each of these domains are occupying 2 lines here. First line is giving you the residuals of the momentum equation, UVW, and the pressure correction. And the mass conservations are quite important because you have to see them kind of dropping between between iterations in the same time step, otherwise the solution might diverge. So continuity is actually something that's very significant, and every CFD analyst focuses with this, and you're highly likely to struggle with this the most, if there would be any struggle at all. This would be the most challenging equation to converge usually. And then you have the temperature, residuals, kinetic energy, turbulent kinetic energy, epsilon, zeta, f. So those are the transport equations that are affiliated with and T2, obviously here is the variance of the turbulent fluctuations of the temperature. So the second line here is just a transport equation of the specific turbulence model you're using. All of these are transport equations, and you're plotting here the residuals of these transport equations. The second one is, if that's lower than its upper domain, then you have the same thing for these two lines in the same iteration. And the third line is for membrane, which doesn't have transport equations at all, because it does not solve any fluid, it does not have any turbulence. So you can see already that the residuals of UVW are zeros, pressure is zero, mass is zero, because there is no fluid that is continuously flowing, but you're kind of transporting temperature as a scalar. You're getting some information from top and bottom, from these upper and lower domain about how the temperature of other domains will affect the solution in time for this current medium or middle membrane. So yeah, that's what you should expect to see in your output file. Let's see where we are now from the solution. So if we tail, we're now currently in time step 25. So don't worry, I expected that this simulation will take some time. Maybe takes about 30 minutes or so, maybe a little bit more to complete these 600 time steps. And that's why I ran this simulation upfront, just to show you the results, or where it's gonna go, and then you can play with it after you watch this episode, and you can reproduce the results yourself, and maybe you can compare them qualitatively or quantitatively. So maybe let's open ParaView and visualize some stuff until we have a good amount of time steps. So if we open this guy, then what you expect here is you have, first of all, PVTU files instead of VTU files. So you're focused to open the VTU files. In this case, you have both of them. So you can always visualize VTU files as well. But what you care about, so VTU here is actually the domain before it was decomposed. That's the whole membrane, for example. But it doesn't show you any representation about processor, right? Because it's not a divided domain. Here it's just that's the domain of the membrane. But if you open the PVTU file, then it gives you a little bit more information about how many processors, and let's close this so you can see the difference. And then if you put processor here, then you can see that the domain is divided into 4, and these are that's the topology of how much each processor is taking from the domain. And you can also visualize, let's say, lower PVTU and upper PVTU as well. You can kind of play around a bit. So it's good actually that we visualized the membrane first, so we can see the interface. Well, we can see already the change in colors, and you're not confused by where is upper, where is lower. So if you can here toggle this a bit, if you toggle this, then you can see that this is the upper domain where the flow is going from west to east, and then you have here the lower domain. When you toggle this, you can see that the flow here is coming as a velocity inlet here to pressure outlet from bottom to top, or south to north. And then you have the membrane in between, which is a solid domain. Then you can always of course visualize the surface with edges, or what type of mesh you have. As you can see, it's quite a nice benchmark to play with, and also to verify some numerics in your code. That's why it was chosen as an illustrative case for this course. So maybe now it's a good time to go and check on our results. So if this is not refreshed, maybe we can go inside and membrane again. Not sure if we have something. Maybe we have something. I mean, since the time step is quite small, let's close these first so nothing gets confused, and then I can show you also where the solution is going, but because I saved the results anyways. So upper, we can take PVTU, take the corresponding, but that's the boundary file. Don't be confused to take the boundary file because it doesn't have the bulk mesh or the internal mesh per se. We have the lower domain, so we have membrane upper and lower at 60 time steps. So you can open all of these, and if you remember from the last time, we mentioned always that you can maybe visualize velocity contours here, there, and so as we mentioned last time, that you can see this pixelized view of the domain because you have the values at the cell center and they're not interpolated. So if you like to smoothen it out, you use cell data to point data, so you can have a smoother picture of how the flow is developing. But anyways, here it's obvious that you have the upper domain, the velocity is coming from left to right. The flow maybe is a bit too early to judge it, but if we visualize maybe pressure, then you can kind of see that there is already the pressure driven flow, the higher pressure here, lower pressure there, and then you're going in that direction. So if I hide this, just so you can see better, the flow is going in this direction with the cursor, and the perpendicular flow is represented here at the bottom, going in that direction, and then you have membrane in between. Maybe it's a bit too early to judge what is happening with membrane, because with membrane what you're expecting is not with the velocity, but you are expecting some changes with temperature, so you need to see, I mean, you can see a little bit of it, that the membrane starts to heat a bit from the left and then from the bottom because of the two perpendicular streams. But it's better maybe if maybe can switch to the case that's been already solved, because this maybe might take some time. So we have the solution here, just to show you how it's gonna look like. It's quite similar to what we've seen already, but just to give you a nicer representation of how the flow will look like. Can again open the PVTU files. Maybe you have here about 250 time steps, which is good. And lower domain, membrane, and upper. So if you have these three files, you can open them. Then when you open, that's the upper domain, the lower domain is here, also marked by velocity contours. You can see already that there's very beautiful jet-like type of flow. Then you have the membrane in between, which is not colored yet. You can toggle those first to see what's happening, but just to keep in mind as a frame of reference, we can put the upper maybe here, and then you can see that the flow is going from left to right before I toggle it. If we toggle off, then you can kind of expect that we have some heating effect here, because the flow is hot, and then it comes to heat this plate from the left, because it's going from from west to east. So we can see that the temperature, I visualized temperature actually on the wrong plane, on the wrong domain. But this is membrane here, and if you choose temperature on this field, you can see already the effect of heating the domain a little bit. If you if you want to see an aggravated picture a bit, then you can rescale your data range from here, and then you can see already that we have some effect of heating coming from the upstream, and then another type of heating perpendicular to it from the lower domain coming also from its upstream. That's pretty much what I wanted to show you for this case. One thing I also wanted to mention here is that the control file is actually very flexible. So it's designed that if you see here, for example, this control file 1, if you pay attention here, this control 1 is describing the input file for the upper domain. So that's the upper domain you have the heat transfer on. You can see that we're missing the keyword for saving the time steps. What's the time interval that upon which we will save our results is missing. And you might have some missing keywords here and there, not because it's bad, but you have always default settings for any control file. So it's very flexible. What you only need to specify for a control file, in essence, is essentially the problem name and the boundary conditions at the end of the file. So this is only what you need to specify for a control file. Anything else is secondary. If you want to constrain the problem, or if you want to make some details in the problem about turbulence modeling, some convergence criteria, some tolerances between pressure and velocity coupling. So you need to specify these details that you want to inflict or you want to impose on your problem as a set point. Apart from that, you have always a backup control parameters that will feed this control file to make it a smooth process. So if you, as we said before, if you forget anything and you want to add a control file that it's not already here, you can go a few steps back. If you go back to documentation, then you will find this all control keywords file. This file contains all the keywords that TFlows has, and we keep updating this file accordingly. So you can always search for a keyword or have a look to see what you need. So you can see already that this is kind of a backup in case something is not defined. Then it takes the default value or the default string from here. So yeah, familiarize yourself with the problem, play with it here and there. Maybe you can change some parameters. You can play with the control file a bit instead of pointing here to control 0. As I said, that the control 0 is the global input file that is controlling the 3 main control files for the 3 domains. You can kind of run this problem on one domain only. So you can make this control file point to this guy only, which is the upper domain, or to the lower domain, or to membrane, and see what happens. You can kind of familiarize yourself with the process and how the code works until you find that it's smooth and everything's clear to you. With that, I guess we can close this case, and you can drop me all your questions. I'm quite sure that you will face some hurdles here and there, since maybe the code is new to you, and especially if you haven't used an open source code before. But don't worry, nothing's too difficult. It all comes with practice, and you will master the code in no time. It just needs that you put your hands in the code and make everything by yourself, so you can get the most benefit out of it. So yeah, with that I would like to thank you, and yeah, see you next time. Bye.